I have to admit, when I first opened the digital folder for today's deep dive, I did something I haven't done in, gosh,
Oh,
years.
yeah. What's that?
I looked at my watch.
Okay.
I don't mean I just glanced at it to see if I was late. I mean, I really looked at it. I just stared at that little second hand ticking away. And I asked myself, is this thing actually measuring anything real?
That is a very heavy existential crisis to be having before we've even had our coffee.
Right. Or is it just some, mechanical toy we built to make ourselves feel better about chaos?
Well, honestly, it's the right frame of mind for this deep dive.
I feel like I need a seatbelt for this one. We cover a lot of wild research on this show, but usually we're talking about things inside the universe.
Right, the contents.
Today we're talking about the container itself. We're looking at a collection of papers and a unified field theory proposal. It's called Scale-Dependent Geometric Field Theory, GTT for short.
Primarily from a researcher named David A. Bessemer.
And if I'm reading this right, he's basically claiming that time, with a capital T, is an illusion.
Well, let's be precise. He's not saying time doesn't exist in the sense that, we don't experience it.
Okay.
He's saying it's not fundamental. It's not the background stage the universe is built on. For Bessemer, time is an emergent property. It's a side effect.
Side effect of what?
Of geometry. The core thesis here is, well, it's audacious. He argues that if you get the shape of the universe right, you don't need a separate dimension called time.
So no fourth dimension in that sense.
Not as a fundamental axis, no. You just get this single, unified formula that explains everything, from why a galaxy spins to why your heart beats.
See, that's where my alarm bells usually start ringing. These theories of everything that pop up online,
I know.
they usually fit on a cocktail napkin, and they fall apart the second you ask a hard question. But you've actually crawled through the math on this. Is this another one of those?
I went in with that exact same skepticism. I was ready to dismiss it. But the difference is precision.
How so?
A crackpot theory just waves its hands when the math gets hard. This theory runs toward the hard math. It takes the most difficult specific numbers in physics things we measure at CERN, and it derives them geometrically.
And the results?
Terrifyingly accurate.
Okay, terrifying accuracy is a phrase I like. So let's unpack this. The whole thing seems to pivot on one deceptively simple formula. T equals delta x over x.
That's the anchor. T equals delta x, x.
The notes call it the logarithmic rate of change. So for those of us who didn't major in calculus, can you translate that? What is the universe doing here?
Okay, let's use an analogy. We normally think of time as a river, right? It just flows, carrying us along.
Right, a clock ticks in an empty room.
This theory says, no, it doesn't. Time is the measurement of change. The formula says time is just the ratio of how much something changed. That's your delta x divided by its current state, which is x.
So if nothing changes, if delta x is zero.
Time is mathematically zero. It stops.
So time isn't the river, it's the wake the boat leaves behind because it moved.
That is a fantastic way to put it. Yes, time is the wake of change. And he applies this to hard physics, like in biology.
The biologically optimized second. I highlighted this entire section because a second has always felt so human, so arbitrary. But he's saying it's not.
He's saying our perception of it isn't. He runs the numbers on the human heart. The average heart has a sort of functional limit of about 3 billion beats in a lifetime.
Which is a terrifyingly finite number, by the way.
It is. Now apply that formula. Let delta x be one single heartbeat. And let x be the total potential, those 3 billion beats.
Okay, so you get a tiny ratio.
You get a very specific ratio. And when you run that through the geometric constants in this theory, it lands almost perfectly on the standard SI second.
Wait, so a second feels like a second to us because that's the processing speed of our biology relative to our own lifespan.
Exactly. We perceive time logarithmically. And you know how time seems to speed up as you get older?
Oh, I feel that every single day.
Yeah.
The years are just flying by.
That's not just in your head. That is Dady or Tibel. Delta XX6 Zedler in action. When you're 5, 1 year is 20% of your total experience. It's huge.
A massive chunk.
But when you're 50, 1 year is just 2%. The geometric value of that time is smaller, so it feels faster.
So this isn't just a psychological trick, it's a mathematical reality.
Yes, and it even applies to AI. The paper talks about negative time in neural networks.
That sounded like sci-fi to me. Are we talking about time travel?
Yeah, not quite. It's more practical. A neural net learns by increasing the weights between neurons. That's positive change, positive time. But what happens when it forgets something?
The weights go down.
The change, delta x, is negative. So for that specific connection, time is literally running backward. Forgetting is a reversal of the time vector.
That is trippy. But okay, speaking of structure, we need to get to the geometric part of this. If time is just a calculation, what's the calculator? The notes describe this very specific shape for the universe. 6 cones.
Right, this is the second pillar. If time is just change, the universe needs a structure to allow that change. Bessemer argues space-time has what he calls cubic symmetry.
Like a box.
Exactly. Up, down, left, right, forward, backward. 6 directions. The theory models space-time as 6 cones projecting out along these axes.
And the angle of these cones was really specific.
30 degrees. The opening angle is exactly 30 degrees.
Why 30? That sounds so random. Why not 45?
That's what I thought. But he argues that 30 degrees is a requirement for a space-filling geometry. It's the angle you need to pack them together without gaps. But here's the kicker.
Go on.
He uses that 30-degree angle to derive the weak mixing angle.
Okay, pause. Weak mixing angle. Remind us what that is.
It's a fundamental number that describes how 2 forces, electromagnetism and the weak nuclear force, mix. We've measured it 1,000 times. It's about 0.231, but we have no idea why it's that number. It's just there.
A dial set to 11 for no reason.
Exactly. And Bessemer takes the geometry of that 30-degree cone, runs the math at the smallest possible scale, the Planck scale, and he gets a value of 0.111.
Which is not 0.231.
Not yet. But in physics, these numbers run. They evolve with energy. When he takes that geometric 0.111 and runs it up to the energy level we can actually measure, it hits 0.231 with 99.9% accuracy.
Okay, that's spooky. So the geometry dictates the physics.
Yes, but the geometry gets even weirder. We assume we live in 3D, right? Length, width, height.
I'm looking at my coffee cup. It looks pretty 3D.
The theory disagrees. It claims the universe is a fractal hologram. It calculates the actual dimension of the universe not as 3, but as 2.79.
2.79 dimensions. How do you even have a decimal point of a dimension?
Think of a sponge. It takes up 3D space, but it's full of holes, right? It's porous. Mathematically, it behaves like it has a dimension less than 3. That's a fractal.
So the universe is a cosmic sponge.
In a way, yeah. If you look at the largest structures we see, the cosmic web of galaxies, that structure fits a dimension of 2.79 way better than it fits a standard 3D model.
And this changes the Big Bang.
Completely. Instead of an infinitely dense point, a singularity, which breaks all our math, it's a fractal seed with a dimension of 2.79. It solves the infinite density problem because you never actually hit 0 volume.
This is a complete rewrite.
Yeah.
But I want to bring it back to the watch. What is the second, really?
Yeah.
The paper proposes this geometric second.
Right. This is where the rubber meets the road. Do you know how we define a second right now?
It's an atomic clock. Something with a cesium atom vibrating a bunch of times.
A very specific bunch of times.
Yeah.
9,192,631,770 oscillations.
Rolls right off the tongue.
It's precise, but it's totally arbitrary. Why cesium? Why that number? Bessemer says, stop using rocks to measure the universe. Use the universe to measure the universe.
So how does he define it?
He connects the Planck scale, the pixel size of reality, with the mass of the electron in that fractal dimension, 2.79. He creates a unit called the geometric second, or sesgiolar.
And how fast is that?
Unbelievably fast. 1 sestor is about 10 to the minus 44 standard seconds. It's the tick rate of reality itself. But the beauty is the conversion factor is mathematically pure. It links everything together.
It's like finding the source code after looking at the user interface for centuries.
That's a great way of putting it.
Okay, so new clock, new shape for the universe. Does it solve any of the big problems? What about entropy? You know, the arrow of time. Why can I break an egg but not unbreak it?
Classic problem. In standard physics, the math works both ways. There's no reason the egg shouldn't unbreak.
But it doesn't.
It doesn't. GTT offers a solution with that log formula again, to D equal delta SS, or where S is entropy.
Meaning time only ticks when entropy increases.
Exactly. The breaking of the egg creates the time. And yeah, you could reverse it, but the probability is something like 1 in 10 to the power of 78. So the geometry of probability creates the arrow of time.
Wow. Okay, what about black holes? General relativity says time freezes at the event horizon.
GTT agrees, but for a much simpler reason. You don't need all the complex tensor calculus of bending space-time. You just apply the formula. As you approach the event horizon, the math just shows that the rate of change hits a limit. Time diverges to infinity.
It freezes.
It freezes. It's a mathematical limit of the formula, not a consequence of bending space.
It seems almost too clean. What about the stuff we can't see? Dark matter and dark energy. We've spent billions looking for ghost particles and found nothing.
And GTT says, stop looking, they aren't there.
That's a bold claim. Galaxies are spinning too fast. Something has to be holding them together.
It's the geometry again. The theory introduces running gravity.
Running as in it changes.
Correct. We learned that big G, the gravitational constant, is a rock-solid number. But this theory argues G-scales. Because of that 2.79 fractal dimension, gravity naturally gets stronger at very large scales, like the edge of a galaxy.
So there's no invisible matter. Gravity itself is just stronger out there.
Exactly. And when you model galaxy rotation with this running gravity, it fits the real-world data with a correlation of 0.952. That's a better fit than most standard dark matter models.
Without inventing any new particles.
Without inventing a single thing. And dark energy. It's just geometric pressure from the fractal unfolding. The sponge is expanding.
Okay, I have to play the skeptic again. This sounds amazing, but anyone can fit a curve to past data. The real test is predicting something new. Does this theory make a testable prediction?
That is the gambit. This is where he puts his neck on the line. He lists about 16 predictions, but one stands out because we are literally building the machine to test it right now.
Okay, what is it?
It's a value for something called isocurvature perturbation.
That's a mouthful.
It refers to tiny fluctuations in the cosmic microwave background, the afterglow of the Big Bang. Standard theory, the textbook stuff, says this number should be basically zero.
And GTT says?
GTT predicts a very specific non-zero number. The logic comes back to the 6 cones. We live in one of them, so we're geometrically blind to the other 5.
We can only see 1/6 of the picture.
Exactly. We only see 1/6 of the total time fluctuations from the early universe. When you apply that 1/6 projection, the theory predicts the isocurvature value will be 0.028.
0.028, not zero.
Not 0.028, plus or minus a tiny margin of error.
And we can measure this.
We will be able to. There's a massive new project called CMBS-4. It's the Next Generation Cosmic Observatory. It's designed to be sensitive enough to see this exact thing.
So when do we get the data?
Around 2035.
So we have a 10-year countdown.
We do. It is a maximally falsifiable prediction. If CMBS-4 turns on and sees 0 or 0.1 or anything else, GTT is dead. It's wrong.
But if the computer spits out 0.028,
then we have to burn the textbooks.
We'd have to accept that our standard model is just a shadow of a deeper geometric reality.
Exactly. It's the Platonic universe. We're in the cave looking at shadows on the wall that we call particles and forces. But the thing casting the shadow is just shape.
This theory says a photon isn't a thing, it's a rotation of the cone's axis. Mass isn't stuff, it's a density of time.
It's all just the universe performing a logarithmic calculation of its own geometry.
It makes you feel small, but also weirdly connected. My heartbeat follows the same logic as the rotation of a galaxy.
It's all the same formula, we're just different variables in the same equation.
Well, I'm going to be watching the news in 2035 very, very closely. 0.028, that's the number to beat.
Nature will decide.
Nature always does. Thanks for walking us through this. This was a heavy one.
My pleasure.
And for you listening, maybe take a look at a clock today and ask yourself, is it measuring time? Or is it just measuring change? We'll see you in the next deep dive.